So I'm a professor in the Department of Astronomy and Astrophysics in UC Santa Cruz. I'm really okay. Um, I'm a user of chemistry. I model planetary atmospheres and planetary interiors in evolution. So I'm a user of chemistry. I'm a user of physics, like the equation of state that build planets. So I was asked to talk about planetary evolution, which is a daunting task to think about what a chemist would want to know about planetary evolution. But tried to put chemistry in mind a little bit while thinking about what we know about exoplanetary systems and also a little bit about the solar system. Okay. Um, One of the things that has come across a few times is really the interesting era that we're in, that we have detailed information about the solar system. In some cases, especially detailed, if we can go to a planet and actually visit it. But in the exoplanet context, by exoplanet, I mean a planet around another star. Those are systems where we cannot know a tremendous amount of detail about any one given planet, but we can look for broad trends comparing planet to planet or system to system. So one of the things that I hope you remember from today is that the vast majority of planets that we're finding, at least so far with the methods we have, are much, much hotter than the planets we have in our own solar system. So these are planets found by the Kepler mission. So the Kepler mission was a specially designed NASA space telescope that found over 4,000 planets. For reasons I don't want to spend a lot of time on, it was mostly focused, it was only able to find planets relatively close to its parent star. Mercury is in an 88-day orbit. Inside of that, we have nothing. Our solar system is entirely empty. It turns out other planetary systems, other stars, much like the sun, prefer perhaps, or certainly make a very large number of planets inside of Mercury's orbit. So the Kepler mission found these 4,000 planets in yellow. Previously known planets are in other colors. These dashed lines show you where Kepler wasn't sensitive to. So it wasn't sensitive to longer periods. It wasn't sensitive to extremely small sizes. So these planets, I'm sure, are there. This is planet radius. This is Earth's radius, Neptune's radius, and Jupiter's radius, about 11 times bigger. This is orbital period in days. Okay? So there are planets the size of Earth, the size of Neptune, that orbit their star in less than a day. So these planets are something like 2,000 degrees Kelvin. Their day sides are probably molten. Their atmospheres might well be rock vapor. Then, of course, there's relatively cooler planets in 10-day orbits, 100-day orbits. These are sorts of orbits that might be more similar to what we think about when we think of planets. So our phase space is much, much larger than we ever imagined it would be 20 years ago when there was just a couple of planets known around other stars. So it's a much larger phase space than found in the solar system, probably much more exotic compositions, and certainly much higher temperatures. So this has come up before, but of course we have to be very mindful about the questions that we try to ask and answer. At Venus, we can go there. Or Titan, for instance, we can go there. We can think about spatial observations, how things change as a function of latitude and longitude. We can think about how things might change over time in a detailed sense. This is a picture of an exoplanet called Beta Pic B. This is a 5 Jupiter mass object that's very young. It's still very warm. It looks like it's, at least for the technology we have today, it's the only planet that we can see orbiting. It's at about a Saturn-like distance from its parent star. The planet that we see is actually just of course, one point of light. We don't have any spatial information. We might only be able to observe it every few months. There's not a lot of time information. And so we're looking at planet-wide average conditions when we look at a point of light. It could actually be worse. So there's a star here that got blocked out, by the way, I should say. It's also, sometimes it's actually worse than that, in that for the vast majority of planets, we don't actually see a point of light. We only see their shadow. So most planets that have been found today have been found via the transit method, where you see a planet eclipse directly in front of its parent star. And that's the only way we know a planet's there. We can see that eclipse happen over and over and over again. That eclipse might happen every day in a one-day orbit. It might happen every 100 days in a 100-day orbit. And it's possible to use a space telescope like Hubble or the forthcoming James Webb to take a spectrum of the light that filters through the planet's atmosphere. And so then we can take a spectrum essentially of the planet's shadow, looking for features like molecules that are absorbing in the planet's atmosphere. So we're looking for things that couldn't possibly be in a star. A hot star wouldn't have, let's say, water vapor, but water vapor and methane are molecules we could perhaps see in the planet's atmosphere as it filters, as that light filters through. That's by far the most common way we've been able to look for atoms, like alkali metals, and also molecules in the planet's atmosphere. And this has only been done for maybe about 25 planets, mostly gas giants like Jupiter, but on very short period orbits. Like, think about Jupiter, but one that receives 10,000 times more energy from its parent star because it's in a 5-day orbit, not a 5-year orbit. So one of the ways we can try to make sense of all this diversity is thinking about categories of planets. So we think planets can mostly be categorized based on where their atmospheres come from. And so atmospheres are important, even though it's a tiny fraction of the planet's mass often. It's the part that we can see. It's the part that we can study. So you can have a primary atmosphere. A primary atmosphere is an atmosphere that's accreted from the protoplanetary disk. So that would be like Jupiter, Saturn, Uranus, and Neptune, and similar exoplanets. They have a hydrogen-helium-dominated atmosphere that they actually accreted via gravity from the nebula. And that actually makes up the vast majority of Jupiter and Saturn's mass. They're essentially almost all atmosphere. 80 to 90% of their mass is hydrogen and helium. Whereas for Uranus and Neptune, they just kind of have a thin skin of hydrogen on top, as I'll show in a later figure. So the atmosphere can be a huge fraction or even almost all of the planet's mass. Whereas a secondary atmosphere is one that's outgassed from the planet's interior. And that's the atmosphere of Venus, Earth, Mars, Titan, and similar exoplanets, where the gas you see today in the atmosphere has been outgassed from the planet's interior or created via some sort of perhaps biological process on the surface. There might well be planets in other planetary systems that are a mix of these two together, but in our planetary system, it's fairly distinct between those two classes. So if we want to look in, we can make pie slices. Like, I assume you guys aren't super familiar with what's going on inside planets as well. This is Jupiter. Jupiter's about 300 Earth masses. We think it has a central core of ice and rock that's maybe 10 or 15 Earth masses. We think that's the part that had the gravity that pulled all this hydrogen and helium down on top of it that formed the planet. The pressure is extremely high. The temperatures are high. So it's a plasma of what people call liquid metallic hydrogen, a sea of protons and electrons, ionized. Whereas the part that we see is colder, and it's molecular hydrogen plus helium. So the surface is quite cold, 166 Kelvin, the visible surface, the cloud tops. But as you go down in deeper, the pressures become much higher and temperature is much larger. So we, of course, feel 1 bar, 10% of the way down, you're already at 1 or 2 megabars in Jupiter. Saturn is somewhat similar. Neptune and Uranus are somewhat similar to each other, where you have maybe 10% of the planet's mass in hydrogen and helium. And then below that, you have a fluid convecting ionic sea. We call those ices because astronomers and planetary scientists have terrible names for things. But it's a fluid convecting ionic sea, and that's probably where the magnetic field is generated. Below that, we think there's a rocky core as well, but most of the planet's mass is ice and rock, fluid. If we go over to an Earth-like planet, this is actually Earth. We have a solid inner core. We have a fluid outer core. That's where Earth's magnetic field is generated. We have the lower mantle that's fairly plasticky over long periods of time. It can convect over long time scales. And we have the upper mantle, which is more rigid. We have our crust that, of course, we live on the top of. So Jupiter itself and Saturn are almost entirely fluid planets, whereas Neptune and Uranus are mostly fluid, and Earth has some fluid, has some plasticky solids, has some solids at the top and bottom. So these are our categories for when we think about exoplanets, we're thinking about things that might or might not look like this. So planets, of course, change over time. I was asked to touch on planet evolution. So planets typically form hot, and they cool off over time. The last stages of rocky planet formation are large Mars-sized things smashing into each other. That is how rocky planets form. And so the initial condition of a rocky planet is always going to be hot and molten, as far as we understand it. So we had a magma ocean, some molten crust, in contact with whatever gases were being outgassed from that magma, probably a lot of water vapor and CO2. That cooling was probably really rapid in the first 10 million years. Things solidify, the crust solidifies. A lot of that gas either has to escape or go somewhere else. It's not that well understood, really, what volatiles are outgassed from rocks. There's been relatively few experiments looking at rocks or meteorites, heating them up, thinking about what gases actually come out of those to test models of planet atmosphere formation. This is a cool plot by Kevin Zonley at NASA Ames looking at the surface temperature over time after the moon forming impact, the last giant impactor that we had, looking at a very hot surface, colder surface, an atmosphere that was mostly made of CO2 and water vapor, steam and CO2. Once your planet cools off enough that the steam condenses into oceans, that collapses your steam atmosphere. Your CO2 can then start to dissolve in your oceans, which is what we have today. Most of our CO2 is in the oceans and the carbonate rocks down below. And that all happens, we think, within the first 100 million years. And then we go on with our relatively temperate planet from there on. It's a pretty cool paper. It's called Earth Evolution of a Habitable Planet. For giant planets, again, they start out hot. You're taking maybe a few hundred Earth masses of hydrogen and helium, very spread out, and you're bringing that all into one spot. So you have a huge change of gravitational potential energy into thermal energy by building a planet. So for Jupiter and Saturn, today they're quite cold, something like 100 Kelvin. When they formed, they were probably more like 1,000 Kelvin for Jupiter, for the visible surface temperature, and Saturn more like 500. And because there's a very large reservoir of that thermal energy, it takes a long time to cool off. So giant planets cool off really for their entire lifetimes. So we have an H2-dominated atmosphere at all times. The cooling is quite prolonged. It's still an active process going on today. We do, however, know that there are giant planets very close to their parent star. Those are called hot Jupiters, which you might have heard of. Those are giant planets that really can't cool off, because if you're in a 5-day orbit around your parent star, you're going to stay hot for your entire lifetime. And although the interior might cool off, your atmosphere stays hot. You would stay arrested in this very hot state for your whole time. But if giant planets can cool off, you see a whole range of temperatures over their lifetimes. So these are model calculations of 1 million years out to 10 billion years. If you imagine a Jupiter-like planet starting at 1 Jupiter mass, when it's young, it's almost 1,000. When it's old, it's down to 100. If you have a 10 Jupiter mass object, which you might call a super Jupiter, it might start around 2,500 degrees and then cool off down to about 300 degrees. So in a very real way, we can look at more massive giant planets at old ages, and we can see representations of what Jupiter probably looked like when it was a much younger planet, because these planets are all cooling off over time. And so if we look at different masses at different ages, we can see representations of what our own Jupiter might have looked like when it was younger and hotter. And these are spectra of real objects. These are called brown dwarfs, which are a lot like giant planets. That's about all I'll say. They form probably in a different way, but they're still hydrogen and helium. They cool off over time. This is a sequence from 2,800 Kelvin down to 600 Kelvin. And the main things that you see is that the chemistry, as you might imagine, changes over that large temperature range. At 2,800 Kelvin, you do have absorption due to water vapor, but you also have atomic lines like calcium, sodium, iron. As you get to cooler and cooler temperatures, you start to form more water vapor. What had been carbon monoxide converts to methane, as I'll show you in a minute. And so the spectrum is something that might look vaguely like a black body. Those that know stars know that stars kind of look like black bodies. As you get to very, very cool temperatures, your spectrum is entirely carved out by strong molecular features, and your spectrum looks totally different. And so these are real objects we can see tracing this cooling off over time. And the way we think this works is by a diagram like this. This is log of the temperature. This is 100 Kelvin, 1,000 Kelvin. This is altitude, so low pressure, high pressure. Real Jupiter is here today in the blue dashed dot line. That's from the Galileo entry probe. If you imagine Jupiter backing it up in time, making it warmer and warmer into the past, let's move to the right. Let's go from 100 Kelvin to 300 to 500 to 800. What would happen is as Jupiter warmed up, its ammonia cloud would vaporize. Instead of ammonia clouds, you'd have ammonia vapor. The next thing that would happen is that your water cloud would then evaporate as well, and then you'd have water vapor. As you got even warmer, your ammonia would then convert to N2. As you got even warmer, your methane would then convert to CO. If you got even warmer, these clouds of iron and silicates would also vaporize as well. And there's very good evidence in hot Jupiters and brown dwarfs that these objects over here really do have clouds of liquid iron droplets and silicate dust that dominate their atmospheres in the same way that ammonia clouds we see are the clouds in Jupiter's atmosphere. So this is a plot showing all the possible cloud species we expect to see in a hydrogen-helium atmosphere as a function of temperature. So the first things to condense are the very refractory things like aluminum, calcium, solids at very high temperature. Then there's iron and the silicate rocks, chromium, crazy things like manganese sulfide, Na2S, KCl, down to water clouds and ammonia clouds down here. So we think planets, as they cool over time, go through all of these cloud species. And if you were in Jupiter and could send a probe very, very deep into Jupiter, you should be able to see all of these clouds in turn going to ever, ever higher pressure. If you could get down to, let's say, 10 kilobars, which is a lot to ask. But these clouds, we expect them to form from chemical arguments. But a lot of these have very poorly understood optical properties, so we don't really have a good feel for how they would affect the spectra. There's lots of uncertainties in what the particle sizes are, what the particle shapes might be, if the grains are pristine or a dirty mixture of these clouds all mixing together, and whether or not grains can catalyze interesting chemical reactions. These are things that we just don't know. I should mention that, of course, these spectra here are relatively low resolution. It has the spectral resolution of these are around not quite 1,000. There's been a lot of work just in the past couple of years of trying to observe exoplanets at a very high spectral resolution of around 100,000. And in that case, you're not looking at molecular bands. You're looking at individual molecular lines. I don't want to talk about the techniques in much detail, but what you expect to see then is if you're looking at the brightness of the planet, you should see individual lines due to, let's say, CO or water vapor. And these are techniques people are applying right now to these very hot planets that we can see today, the 2,000 Kelvin planets. But the same techniques, really, people want to apply that to more Earth-like worlds in the next decade or two. So this is a main science case for these extremely large telescopes, ELTs. So right now, funding's being sought to build 3 telescopes that are all around 30 meters across in terms of their main primary mirror. There's a European ELT, and there's 2 American-based collaborations. One's called the 30-meter telescope. One's called the Giant Magellan Telescope. And these dwarf the largest current telescopes, the Keck telescopes in Hawaii, that have a 10-meter mirror. So we have an urgent need, really, for lab studies of line positions and line strengths up to, as I mentioned, these very unusually high temperatures for planets, up to about 2,500 degrees for these common molecules like water vapor, CO, CO2, methane. So I do have a few slides left, but I think I'm doing pretty well with time. I also want to mention on this topic of planet evolution that UV-driven photochemistry can actually drive divergent planet evolution. Of course, there's a there's a story we tell ourselves about how we think Earth and Venus ended up so different, even though they probably formed in a very similar way. And that's that Venus is so warm that even if it had that's so warm that it's lost all of its water vapor to space. It's so warm that the water was never in a liquid phase. It was in the vapor phase. When water vapor gets to the top of the atmosphere, you can break it apart by ultraviolet light. The oxygen stays behind. The hydrogen goes away. Estimates suggest Earth and Venus have similar amounts of CO2 and nitrogen. We have all nitrogen in our atmosphere, basically. Venus has about the same amount of nitrogen in its own atmosphere, but it's dwarfed by the CO2 that Venus has in its atmosphere, whereas our CO2 is mostly tied up in carbonate rocks on the ocean floor because we have an ocean. In a very different way, we see in the exoplanet context, we can see divergent planetary evolution. This is a plot of how common different size planets are. So these are the gas giants, inherently not very common, large planets. What the Kepler mission showed us is that relatively small planets, about 2.5 times the size of Earth, are incredibly common on short period orbits. And then also Earth-sized planets are relatively common. There's this very interesting valley that was just discovered in the past year. And it shows that we think it looks like planets are diverging into two populations. One population is one that is able to keep a thin skin of hydrogen and helium atmosphere, and one is one where there's no hydrogen and helium left over. We think this might be how they formed, but I actually think it's actually a divergent population, that this gap actually grows as systems age. This is a discovery just in the past year in exoplanets. So my last thing I want to mention is just another topic in atmospheric evolution that depends on our knowledge of chemistry and opacities. This is what people call the fate-young sun problem, or fate-young sun paradox. The idea is that the sun was actually much less luminous when it was young. When the planets formed, the sun was only about 30% as bright as it is today. So the right axis is the solar luminosity, the solar brightness, billions of years ago. So this would be this black curve here, and today it's our normal brightness. You can calculate a model for how good Earth's greenhouse effect is. And you can go backwards in time and think about, if the sun was 30% dimmer, would our surface actually be warm enough to have liquid water? And if you use Earth's current atmosphere, the answer is no. You go back in time, this is temperature of the surface, you go back about 2 billion years, and the surface temperature would be so cold that the surface of the Earth would be frozen. But yet there's very good geochemical evidence for us having liquid water at much earlier ages. There's a very similar argument for Mars. Mars is even further away from the sun, even bigger problem. But yet there's valley networks that clearly indicate tremendous amounts of liquid water on Mars at a very old age. And so at a very young system. So the question is, what kind of atmosphere do these planets have to have at this young age so they'd have a much stronger greenhouse effect to keep their surface warm when they were young? This has been an area of a lot of work over the past 30 plus years trying to sort this out. I just want to mention there was a paper that came out just this past year that realized there was a huge error in the opacities people had been using. It turns out that, of course, molecules have opacity, but then when they collide with each other, you can get collision-induced absorption. That actually can change the molecular bands that happen when these collisions happen, because they, of course, these molecules bump each other and they disturb each other's electron clouds. And so as a consumer, people who model atmospheres, we use these coefficients in terms of how opaque these molecules are. And so this is a calculation of the surface temperature of Mars as a function of how much methane might have been in the early atmosphere, as a function of how high of a pressure the atmosphere might have been. And the basic idea is to compare, let's say, this blue curve to this dashed blue curve, where there's about a 30-degree difference in temperature. And it turns out once folks used more appropriate opacities, they could warm up the surface of Mars by about 30 degrees. And the suggestion was made, we strongly encourage experimental investigation on these sorts of opacities in the future, which I know isn't exactly chemistry per se, but it's laboratory work that our field needs. My last slide is really an advertisement. So I kind of cherry-picked a few topics of interest today that I thought would be interesting. But there's a white paper that I led with many, many other authors about 2 years ago. It's on the archive. It's a white paper about laboratory work in the aid of understanding exoplanet atmospheres. And it was put together by this group called the Nexus. This is a group of people affiliated with NASA who are interested in exoplanet atmospheres. This is the link for the paper. I can always email that out if you're interested. And I have a certain amount of expertise, but this group on here has a much wider expertise than I have alone. But we found a list of about 6 important categories where we think laboratory work is helpful, very helpful. So one is molecular opacity line lists, extended databases for this collision-induced absorption, laboratory studies of haze and condensate formation, expanded databases of chemical reaction rates, measurements of gas, photoabsorption cross-sections, and vapor pressures, all at typically temperatures and pressures higher than that of the Earth. There's certainly temperatures higher than that of the Earth. And just to give a shout out for the things we're going to see in the future. So like all astronomers, we're patiently waiting for the James Webb Space Telescope to launch. It's going to deliver spectra from the red optical to the mid-infrared. There's going to be a huge fight's not the right word. Everyone wants to use this telescope, so fields will be pitted against each other. And it's unknown exactly how much telescope time we'll actually get to do exoplanet atmospheres. But over the course of 5 or 10 years, I expect we can get very nice, high-quality spectra for maybe something like around 100 exoplanets. The gas giants are going to be the ones that are easiest to study. And so for those planets, we'll typically get more and better spectra. But there are some incredibly interesting systems, like one called TRAPPIST-1, which is around a very small faint star, where there's 7 planets that are all around the size of Earth. And all 7 of these planets pass directly in front of their parent star. And for these objects, it would be a phenomenal experiment in comparative planetary science to look at how these 7 planets have diverged over their lifetime. The innermost one is a little bit cooler than Venus. This guy's a little bit cooler than Venus. These 3 are kind of around Earth's temperature, warmer and colder, and these 2 are cooler than the Earth. And so if we actually can get spectra of all these objects, it will be an amazing experiment to compare to our own planetary system. And so to conclude, the exoplanet context greatly expands our phase space, nearly all of it at higher temperatures than we have in our own solar system. The details of the solar system are essential to complement the larger astronomical perspective where we can't know as much about any individual planet. Planetary evolution can be most readily viewed through the lens of the atmosphere because that's the part we see, even though it would be great to also see what's happening in the interior. And the community is working on a needs list for future progress from chemists and physicists summarized in that paper I mentioned before. Happy to take questions.
Was really fascinating. Quick question on the fast traveling. I have read the TRAPPIST-1 paper when it came out a year and a half ago. And I remember these planets have orbital periods of 12 days or something like that, right? They're screaming around their star. How do I think about the fluid dynamics of an atmosphere under that condition as opposed to something leisurely like what we are enjoying?
Yeah. So that parent star is 1,000th the brightness of the sun. It's very small and faint. And so the orbits are, I think, 3 to 40 days, basically. They're all packed in there. If you were on one planet, you could see the phases of the other one with your own eye. You wouldn't even need a telescope. We think the innermost ones are probably tidally locked, just like the moon is to the Earth. So although they're moving with a high velocity in their orbits, their rotational velocity, which really drives like the Coriolis force, they're not probably really rapid rotators, so their circulation might be more benign. So Venus has a much more sluggish circulation than we do because it's a slower rotator.
All right, well, let's thank John.
Sure.